Hello, so in today's class we will see when you have two distinct characteristic values, so how to obtain the solution. So suppose you have two distinct eigenvalues, lambda 1 and lambda 2. The two distinct eigenvalues of coefficient matrix A and when the eigenvalues are distinct, so we know that there will be a distinct pair of eigenvectors and they will be linearly independent. We have seen the result in the previous class, and let me call the eigenvectors as alpha 1 and alpha 2. So let alpha 1 and alpha 2 be the corresponding eigenvectors of A. Then the two distinct vector functions are അപ്പോൾ നമ്മൾ problem solve ചെയ്യുമ്പോൾ we'll take the trial solution. നമ്മൾ x equal to alpha 1 e raised to lambda t and y equal to alpha 2 e raised to lambda t കൊടുത്തു കഴിയുമ്പോഴാണ് നമുക്ക് കിട്ടുന്ന characteristic equation roots eigenvalues ആയിരിക്കും, and you will get alpha 1 alpha 2 values. They will be the components of this eigenvectors. So the two distinct vector functions we are going to get, so let us call it as x1. So x1 of t is first eigenvector, alpha 1 into e raised to lambda 1 t. This is the first eigenvalue, and the second vector function is x2 of t. So that is the രണ്ടാമത്തെ eigenvector varum. So that is alpha 2 e raised to the second eigenvalue e raised to lambda 2 t. Now we know that since lambda 1 is lambda 1 and lambda 2 eigenvalue ആണ് of the coefficient matrix A, and alpha 1 and alpha 2 are the corresponding vectors. Now this alpha 1 and alpha 2, so alpha 1 and alpha 2 satisfies the equation. So we have a relation involving the eigenvalue and eigenvector, so they will satisfy the equation A alpha 1. Ax will be equal to lambda x. A lambda alpha 1 എന്ന് പറയുന്നത് that will be equal to lambda 1 alpha 1, and we will have A alpha 2 will be equal to lambda 2 alpha 2. So lambda 1 and lambda 2 are the eigenvalues corresponding to the eigenvector lambda 1 and lambda 2. So therefore it will satisfy this equation. ഇനി നമുക്ക് solution കണ്ടുപിടിക്കുമ്പോൾ, so we have got x1 and x2. So x1 ഉം x2 ഉം solutions ആയിരിക്കണം. So our aim is to solve for the equation dx by dt equal to ax. So we have got x1 and x2. So we need to check whether x1 and x2 random solutions ആണോ. ഇനി അത് solutions ആണെങ്കിൽ അത് രണ്ടും linearly independent solutions ആണോ. അങ്ങനെയാണെങ്കിൽ we can go and write the general solution. So general solution will be c1 x1 plus c2 x2. So we will look in at two things. First of all, whether x1 and x2 their solutions or not, and they are linearly independent or not. അപ്പോൾ solution ആണെങ്കിൽ it will satisfy the equation dx by dt equal to ax. So let us look at the equation first. So when you take d x1 of t by dt, so that is going to be equal to x1 of t എന്ന് പറയുന്നത് that is equal to alpha 1 e raised to lambda 1 t. So when you take the derivative of this, that will be equal to alpha 1 constant vector aanu. Then this part contains t, so the derivative is going to be lambda 1 e raised to lambda 1 t. So this will be equal to so alpha 1 you have lambda 1 alpha 1, so lambda 1 alpha 1 is equal to a alpha 1, so we are going to get a alpha 1 e raised to lambda 1 t കാരണം eigen value eigen vector തമ്മിലുള്ള again relation എടുക്കുക. So a alpha 1 will be equal to lambda 1 alpha 1. അപ്പോൾ lambda 1 alpha 1 നെ എനിക്ക് a alpha 1 വെച്ച് replace ചെയ്യാം. So we are going to get again alpha 1 e raised to lambda 1 t. So that is a x1 of t. So therefore x1 of t, sorry, not this x1. Okay, so that is x1 of t. So you have a x1 of t. So therefore x1 of t satisfies the equation dx by dt equal to ax. And similarly you can show that. So similarly x2 of t also satisfies the above equation. So hence x1 of t and x2 of t are solutions. So they are solutions of dx by dt equal to ax. And now we need to check whether these solutions are linearly independent or not. So for that, let us find the wrong scan of x1 and x2. So if they are linearly independent, determinant എടുക്കുമ്പോൾ 0 ആയിരിക്കണം. It must not equal to 0 ആയിരിക്കണം independent ആവണമെങ്കിൽ. So you will get alpha 1 e raised to lambda 1 t, then alpha 2 e raised to lambda 1 t, and alpha 1 e raised to lambda 2 t, then alpha 2 e raised to lambda 2 t. So we can take lambda 1 and lambda 2 outside. So e raised to lambda 1 plus lambda 2 t into determinant എടുക്കുമ്പോൾ determinant will be alpha 1 alpha 1 alpha 2 alpha 2. So since these are components of your eigenvectors, നമ്മുടെ eigenvectors are linearly independent ആണ്. So this determinant will be not equal to 0. So determinant alpha 1 alpha 1 alpha 2 alpha 2 is not equal to 0 since the eigenvectors, so alpha 1 and alpha 2 are linearly independent. And again, and also e raised to, when you take lambda 1 plus lambda 2 t, that is always not equal to 0. Karnam exponential function is always not equal to 0. So that implies a wrong scan of x1 and x2 is not equal to 0. So therefore x1 and x2 are linearly independent. So Therefore, the general solution is going to be equal to, so that is x of t. So x of t is c1 x1 plus c2 x2. So that is the required general solution where c1 and c2 are arbitrary constants. So this is the form of general solution when you have distinct eigenvalues. And let us summarize this as a theorem. So consider the homogeneous linear system. So take dx1 by dt equal to a11x1 plus a12x2 and dx2 by dt equal to a21x1 plus a22x2, or that is the vector differential equation dx by dt equal to Ax. So where A is the matrix A11, A12, A21, A22, and X is the vector X1, X2. And suppose the characteristic values lambda 1 and lambda 2 are distinct, and let us call this alpha 1 and alpha 2 be the pair of respective characteristic vectors. Pair of respective characteristic vectors of A. Then on every real interval the vector functions defined by alpha 1 e raised to lambda 1 t and alpha 2 e raised to lambda 2 t form a linearly independent set of solutions of the system dx by dt equal to ax and x equal to c1 alpha 1 e raised to lambda 1 t plus c2 alpha 2 e raised to lambda 2 t is the general solution, where c1, c2 are arbitrary constants. So that is the form of general solutions when you have distinct eigenvalues. So in the next session we will see a few problems on finding the solution.